Alright everyone, let's begin. So today I was thinking I might do a little bit of... So I saw that the exam grades came back, and you know, it was remarkably not great, so let's go over some of the problems. Okay? So I think the Futurama problem, I think the average was pretty good. Oh, homework 5. Never mind. Let's go over homework 5 instead. That's what I meant anyway. Thanks, Sean. Sean knows more than I do anyway, so... Okay. Yeah, my hope is that maybe the first midterm will turn out better than the homework 5. I guess homework, it was pretty bad. So... Okay, so let's look at the anagram distance problem, and then we'll return to recursion. So, let's see. We should write a function called anagrams that... Okay, let's do that. And what do we do? It determines the distance between them. Oh, okay. Let's check on that. So... let's see. Okay. Can't find the email. Okay, yeah, I'm not gonna waste any more time looking for an email. Okay, so, fair enough. Okay. Will we have back-to-back projects and exams? Yeah, more or less. So after homework 6, you'll have project 2 and exam 2, and then after that you'll have project 3, and then you'll have the final. And that's really what's left in the class. So, okay, let's do this anagram distance. So basically, the anagram distance is like if it's the same word up to a permutation, it's anagram distance 0. If you have to add one letter to a word, that's distance 1. If you have to change a letter, because basically what that's doing is it's like removing a letter and changing it to a different letter, that's distance 2. Here, I guess you have to, what do you have to do? You have to remove an I and a G and replace them. Oh, and the E doesn't match either, so it's distance 3. Okay. And, yeah, and then Q and NQ, you have to add 2 letters, so that's distance 2. So, now that we know all that, let's implement it. So, let's do that, and then let us copy paste this code here. All right. Let's just do this, and there we go. All right, better. Now let's call this anagram tester. And so good, we're on board. Okay, so let's look at this thing then. So how did I do it at least? Let's just call something first word letters equals a new dictionary, and then I'll have second word letters equals a new dictionary. This is just kind of the way that I thought to do it. And so what I did was I basically just added all the letters in words into the dictionary. So what I said is for letter in, say, word 1, right? And that'll split the thing by character. What I'm going to do is I'm going to say something like first word letters, letter, equals, oh wait, sorry. If letter is in first word letters, then we add 1, else we set the number of letters equal to 1. Like this. Okay, So basically what this is doing is it's counting up, and we'll see after, in the end, we'll just print out the first word letters and just see what happens. And then we do the same thing with the second word. Everything is the same except it's second word letters. Second, word 2. And then the anagram distance is just going to be the difference. So for, I guess what should I say? Letter in first word letters. You know, if letter in second word letters. What should I, is this the right way to do it? Is this the smartest way to do it? I feel like I'm forgetting how I did it in my actual solution. Then you can say first word letters letter minus second word letters letter. And then I guess you can take the absolute value of that. So I allowed you to use the absolute value if you wanted, or you can test if it's negative or something and then flip it. So difference plus equals. So let's set the difference equals 0. I guess I actually should call it distance. Did I? Oh, yes I did. So, and then I guess we can do this way, right? So if the letters match, I guess else what we can do is just say distance plus equals the number of things in the... I'm really thinking that I did this smarter in my actual solution, right? Because what I'm doing here is I'm counting up the number of ways the distance... Oh, yeah, you know what? I'm stupid. This is a dumb way to do it. Dumb way. But let's keep going. Yeah. Anyway, this is a way to do it. So then here you have to think about the condition that you would need. You would need something like, if the letter is not in the first word letters, then we can do distance plus equals the, I guess, absolute value. I guess you don't need absolute value on this, so it doesn't matter. You know, just second. There we go. Alright, so this is a stupid way to do it because it's way too long for what's required. But, I mean, it's definitely a way to do it. And as you see, I didn't really think about it too hard, and that's why I came up with this bad solution. Oh, it's not really terrible. I mean, it's okay. It's just a little bit too long. But anyway, the point is, I counted up all the letters in the first word. I counted up all the letters in the second word by their letter. And then what I did was I said, if the letters match, right? So if the letter is both in the first word and in the second word, then we take the absolute value of the distance, right? So if it's an actual anagram, all of these should be 0, right? And then, of course, what is this else? This else is saying if the letter is in the first word but not in the second word, then I just add in the number of times we counted that letter in the first word, right? And that's because, you know, if we just have, say we have the two words are like happy and happiness, right? So the thing is that HAPP match, but then this Y, this INESS don't match. What about removing all letters that are the same and adding what is left? That's also, you can also do that. Yeah, you can also do that. So, well, I mean, removing, I guess that's the only thing. Well, you know what, I guess, yeah, so that's, good question. Yeah, I guess that's another way to do this problem that I didn't even think about. But anyway, so this is, let's say, first way. Okay, and so this is one way to do the problem, which is not actually my favorite way. I accidented into this solution. So let's do it another way. So anagram distance trial 2, right? So let's go again. Basically, I'm going to do everything the same here. The only thing I'm going to do that's different is I'm going to go through all the letters in the first word, and instead of having 2 different dictionaries, we're just going to have word letters is equal to a new dictionary. And so what I'm going to do here is I'm going to say if the letter is in here, do this. If the letter's in here, just set it equal to 1. There we go. And now for word 2, instead of having 2 dictionaries, this is, I think, probably what I did, is for letter in word 2, if the letter is in the word letters, we subtract 1. Else we set it equal to -1, right? And so what that's going to do is it's just going to fix all of our problems for us, because now all we have to do is say distance equals 0, and then what we do is we say for letter in word letters, and we say distance plus equals absolute value word letters letter. And so then we just return distance. And that saves us a huge amount of code. Yep. I definitely threw a semicolon on the end of that, but didn't need it. So that's another way to do it. And I think, yeah, so another way to do it is kind of using, if you want to use lists, you could do it maybe this is, we'll call this trial 3, or third try. So instead of using a dictionary, one way that you could do it is to say split word equals list of word 1, and split word 2 equals list of word 2, right? And then you could actually use the list remove feature, right? So you can say for letter in word 2, I guess you could do something like if letter in split word 1, and of course I need to change this to split word 1 rather than 2, then what we can do is we can do split word 1 dot remove letter. And so you can do that, else, you need this else, right? You have to do distance plus equals 1, right? Because if you can't remove that letter, then that means that the letter, either you removed all of them or it was never in the word, and so you need to start incrementing the distance. And then I guess you have to do the same thing for the other direction, so you got to go the other way. So something like this. For letter in word 1, if letter in split word 2, split word 2 dot remove letter, else distance plus equals 1. And then the only thing you have to do now is there could be stuff that's left. Could there be? Or is this enough? Let's think about it. Let's try it out. Let's do it. So these aren't exam solutions, these are. Okay, so let's enter happy and potty. Distance 0, pots, stop. Distance 0, let's enter net, not. Distance 2, yep, that's right. No and not. Distance 1. Okay, so that's actually a pretty good solution too. So basically what this is doing is that it's going through word 1 and it's removing all the things that are in word 2, or I should say this. It's going through word 2 and it's removing them all from the list that we made of word 1. If it can't remove it, it adds 1 to the distance. And then here for letter in word 1, you know, the same thing. You just go and do the exact same thing, just with 1 and 2 reversed. And you see that that does produce the correct answers. Hopefully, right? Okay, cool. So I think we've spent way too long on this one particular problem, but I think it's a good because I've shown you, what, 3 different solutions. Here's the solution that I came up with when I wasn't thinking, but you see it still works. And then this one's the actual solution that I wrote when I was creating the problem. I just completely forgot that solution. And then here is, I think, the solution that other people were telling me that they were, which is also fine. So you can use lists, you can use dictionaries, whatever. Okay, so let's do another problem. Major key. Oh, I like this problem. So basically, let me copy paste this. Actually, let me copy paste this into a notepad. And then let me do a little bit of find replacing. So I'm going to do this. And then I'm going to say, I'm going to replace this, a comma, with parentheses. There we go. Let's replace all. Perfect. Perfect. There we go. Done. Now I've got my list that I can hard code into Python. So let's talk about it. So basically, a major scale does a whole step, half step. Let's see. Was it required to have the last key to be repeat of the first key? Oh, in general, no. I think the way that I did the sample output here, if you notice, like G, A, B, C, D, E, F sharp, and I didn't have G. I think you're allowed to have it, but it wasn't required. So let's talk about music, right? Let's talk about music scales. I forget what the function's supposed to be called, but it doesn't matter. I think it was supposed to be called major key. So here what we're going to do is we're going to define a little constant, and here's going to be music notes, right, equals there. And then what's the information that we get? I totally forget. What's the information that we get? We're going to be told, let's see, what do we do? We're going to be given a starting note. Okay, cool. So what I would do is I'd find the starting index. Yeah, so let's input what note do you want to start with? And so then I'll say note equals blah. And so then what I'm going to do is I'm going to say for I in range len music notes. And then what we'll do is we'll just say start index is equal to, say 0 for now, and then we'll say if, let's just make it -1. So this will help us out. You'll see why in just a second. If note is equal to, let's do note dot upper just to help ourselves out, is equal to music notes I, then start index is, or let's just call it start note, is equal to I, and there we are. Okay, so now if the start note is still equal to -1, then we print out, nope, this was not a note, right? And then we return. Okay. Basically what that's going to do is it's going to boot us out of this function, right? So this finds us the index of the starting note. And then, what? And then, okay, so now comes for me, the easy part. I hate all this other crap where you have to find an index or you have to do all the error checking. This is the part that I like, right? And so basically we can hard code, we can say major scale is equal to, say, and what I'm going to do is I'm going to say 2, 2, 1, 2, 2, 2, 1, like this. Okay? And the reason is because we know that a major scale is a whole step, then a whole step, then a half step, then a whole step, whole step, whole step, half step. And the thing that we notice about a whole step is that it steps 2 notes, right? Because in the middle, there are sharps and flats. So what that means is that a whole step is 2 steps, a half step will just be 1 step. And then what we get to do here is, and let's see, how do they want the output? Okay, we can do that. So we can say for I in, or let's just say, yeah, for step in range major, or no, we don't even have to do that, in major scale. What we can do is we can print out, let's say current is equal to start note. You can actually just use the same variable both times, that I'm creating a new one. Let's print out, let's see, music notes current, current, and then let's increment current plus equals step, and then to make sure that we don't go past the limit, we have to mod it by the length of what? Music notes. So that's basically how we do it. We just add something to the step, and then we mod by the music notes. You can also do this, the other way to do it would just be current is equal to current plus step mod length music notes, right? You can also do that. Okay, cool. And so now what we're going to do is we're going to print this out with the end is equal to maybe just a space, and I think we're done, right? And then we're done. Function over. Let's see if this works, right? So let's call, let's say, while, I think I actually, I would look at the sample output, because the sample output tells you kind of what I expect, and so it'll tell you a bit more about, like if you look at the sample output, it kind of tells you what I'm looking for, right? And you might understand the problem statement better. Like here, you see a whole bunch of stuff about music notes, and maybe you don't understand this part, so then I would say look at the sample output, and then ask yourself, do I understand this part? And just, will jobs? No, probably not. So the answer is that almost certainly not, but that's not the point, right? Like the point is that when you're actually working in a job, you are not going to be expected to produce, like take a certain piece of text input and produce an exact piece of text input that we're looking for. Like that's not really how a job works. Like in a job, we're gonna, you'd be asked, hey, can you write a feature that makes sure that users, like, that encrypts the passwords of users as they enter them, or can you write a feature that allows a user to do a certain thing, right? It's going to be way more open-ended. And so the thing is that for actual jobs, like, you're not going to be given this, but you're also not going to be graded on the same kind of metric, right? The metric that you're going to be used to, that people are going to look at when you're actually doing work is like, are you getting towards like the overall goal of what it is? Even if you change how they want things to look, they might be like, oh, well, what you're doing is better, or like, hey, we want this change, right? Whereas like with a homework problem, it's really hard to know. So I would say use the sample input to your advantage. Okay, so let's run this thing. So let's start with C and see what happens. Nice, C, D, E, F, G, A, B. And so the last thing, if you had to repeat it again, you could always just, if you felt like repeating the start note, you could just repeat the that, and then you would get, here you would, if you started that, you would get C, D, E, F, G, A, B, C. So yeah, so let's see, D, right? D should be D, E, F sharp, G, A, B, C sharp, D, right? D was not a note. Wait, D's not a note. Oh, crap. Look, there's extra spaces in there, and I never took them out. Okay, let's fix this. Dot strip. Dot strip. There we go. There we go. Now I don't even have to fix the spaces. We're just hammering it with dot strip on both sides. You see, yeah, I know. But you see, it's not gonna matter now because I just stripped them off. No, it's okay. Like, that was my bad. I did the find replace, and I didn't realize that there were extra little spaces here. And by didn't realize, I mean completely ignored. So let's start with F, right? So F is going to be a whole step, so FG, right, whole step, and then technically I think normally we would call this B flat, but we'll call it A sharp, right? So F, G, A sharp, C, D, E, F. So this is correct. Musically, we normally call this B flat when we're talking about the F major scale, but you know, the actual question you would ask is, who cares? And we currently don't. So, and let's try another one. Let's say G, right? G should be the scale with the F sharp, right? So yeah, G has the F sharp, so there we are. I like this problem. It's a cute little problem. Okay, let's do another problem. And I'll release these solutions. Yeah, we're doing matching shapes now. Everybody loved matching shapes. The performance on matching shapes was so good that it inspired me to review the homework. So, so I know that the vast majority of you are going to kick yourselves when you see, so when you see what I do for this problem, you're going to be like, oh, well, that was dumb. Yeah, no, I'm just going to do the extra credit. So watch this. So here's the total solution of the problem, okay? And then I'll do the plus sign thing. So let's see, grid, and so for J in range len grid. Okay, so I'm just going through the grid piece by piece. Technically, I'll do this slightly different than so I'm going through every position, and now now I'm going to ask the question, what if IJ is the start position of the shape, right? What if we can fit the shape into the starting position there? So what we do is we say, for K, maybe shape I in range len, and what's the thing called shape? And for shape J in range len shape. Shape 0. Or maybe I'll just yeah, shape on shape I. That's technically correct. The best kind of correct. So now that we have these four loops, what we're going to do is we're going to say, okay, if I plus, and then let's say found equals true, okay? So we're going to assume that we find it, and then what I'm going to do is if I plus shape I is less than the length of the grid, and J plus shape J is less than the length of grid I, yep. This is just making sure that we don't get any index errors. The problem average was 2 out of 10 on this. I think that was either the mean or the median, so it was really terrible. I mean, I'd use words like abysmal, horrific, disastrous. You know, fill in the blank with any words you like. So then, remember that the point of this problem was that if the place is empty, right? So if the grid at I plus shape I and j plus shape j is empty. So I'm going to say if not, right? Is that right? Yeah, because if it's empty, or if it's an empty string, then we're good. But if it's not empty, so this is if the position is not empty, but we need that position, right? So what I'm going to do is I'm going to say and the shape at shape I, shape j, right? Then we're going to say found is equal to false. And then basically if found, return true, and then here we'll just return false. And that's it. So this is basically the line that you need. You need to remember, or you need to realize that what you have to do here, and what this is actually doing, is it's literally just trying to put the shape in at that position. And it's just trying to put it, it's just saying like, okay, if I and j is the start position, and we can do more than this. We can print position found at right. Yep. So we can do something like this. Okay, so let's do this. Let's see. Let's take some of these examples, okay? And let's make sure it works. Because it could possibly just not work. Right, so this one we want it to return false, because what happens is we try to stick in an x, and the problem is there's no blank spaces in here, so it should scan through and find nothing. So let's see what happens. And then here, there is one blank space, so it should stick it in here. And then here, there's like the Tetris L shape, or like it's like a backwards L shape. And we see that there is space here. There's actually an extra little bit here, but there is space here. So hopefully what we're going to see is 0, 2 popping out. It should print 0, 2, and oh no, actually it should print 0, 1, because it's going to match here, and it's going to put the shape in here. And since this is blank on the shape and this is not blank here, then that's what it should do. So let's see what happens. Position found at 1, 1. Position found at, that's correct. And then here, position found at 0, 1, which is correct. And then here, we just have like this star pattern, and you see that you can stick the star pattern in here. But there's actually multiple places that you can stick the star pattern in. So, you know. So let's make a this is not part of the problem. Like this is a little bit extra, but this will help us out a little bit. So you see here that for this last one, we actually had like just a huge number of possible places that you could actually insert the shape, and technically we found all of them. Now if we just, instead of doing this, if we just return true here, it'll just find the first one and return. But here we actually found all the different positions where we can stick the thing in. Cool. So let's do the actual problem from the problem statement that wasn't actually. So this was the extra credit version, right? So let's call this is there space EC. And now let's just do the regular is there space, right? And the whole point is you just have to fill in exactly this shape. So it's almost the same, except it's a bit easier. So all you have to do here is wherever you are, you can delete all these for loops. Yeah, we can do this with way less. We can do this with a few less lines, and we can basically just say that if, and then we can say if, say, shape. Well, okay, so we know where the shape is because it's like hard coded now. Just imagine it's hard coded. So basically, if what? what are these positions that we actually need here? The positions are 0, 1, and then we need 1, 0, 1, 1, and 1, 2. So here's an interesting way to do it. We can actually do a for loop through all the positions we need in this list. 0, 1, 1, 0, 1, 1, and 1, 2. Actually, this might be a little advanced. Let's just, instead of doing that, let's just say if grid at I j plus 1, or I guess really we should say if not grid, and not grid I plus 1 j, let's do a whole bunch of if statements, and not I plus 2 j, and not, wait, what was I doing again? Oh, we need, crap, I did this totally wrong. So this is I plus 1 j plus 1, and then this will be I plus 1 j plus 2. So, and then if that's the case, that's what we actually want, so we can just return true here. And then here, we can just return false. So I guess this is probably the shortest path to the solution. What's wrong with elif? Nothing's wrong with elif, I just didn't use it. I just did a whole bunch of ands, right? And I guess technically you could always De Morgan's law this thing and pull out all the knots and replace all this with ors and all that stuff. But whatever. So this is basically it. Why not j minus 1? Because if you look at the shape and we pretend that this is position ij, right? So if this is at position ij, then this is position I j plus 1, right? That's what this position is. This is position I plus 1 j. This is position I plus 1 j plus 1, and this is position I plus 1 j plus 2. And those are what the positions are. So that's what does what meet coding standards. Yeah, so basically this means we need I j plus 1. Oh yeah, there's no rule about the number of ands you can have. And I mean, the only thing it might violate is like the 80 line restriction, which of course I totally ignore anyway, but if you're offended by that, you can just do this, right? And then there's no problem. Okay. So alright, so that's basically the solution that I had, or I don't know if I actually ever wrote the solution down. I think I probably didn't. So, because initially the extra credit was the original problem, so my solution was this thing, and then I never actually bothered to write a simplified solution because I didn't really need it. Because the more general solution works for the simpler case too. So anyway, okay. Let's go through weave lists. So what does weave lists do? Almost certainly. So in order to weave the lists, let's say min length is equal to, let's say if the length of the first list is less than the length of the second list, then we'll just make this the length of the first list, else min length equals length of second list. Okay, cool. Yeah, we're still on homework. I figure I really should go over all this because the performance on this assignment was bad. So I need to fix that. Or do something about it. Not 100% sure what. Anyway, but the point is that here I'm finding the min length. It'd be nice, I should just have legalized the min keyword, because then you could just do len first list, second list, you know, and you could have been really lazy. So this is the alternate, but unfortunately min is currently forbidden, so I don't think it's, I think I actually should legalize it, but the whole point is, yeah, whatever. So, anyway, so what you're going to do is you're going to say for I in range up to min length, right? And then what you're going to do is you're going to say my new list, right, equals empty list, new list dot append first list at I, new list dot append second list at I. And then here, we can just append the rest of the stuff onto the end, right? So what we can do, and so basically the whole point of the weave lists problem was to go, you know, first list, second list, first list, second list, first list, second list, until you get to the end, right? Then just dump the rest. And so here what I'm going to do is I'm actually going to cheat a little bit and say for j in range min length to the length of the first list, and then what we're going to do is new list dot append first list j, and then I'm going to do the same thing for the second list. And I want to show you why this is a little bit of a tricky thing that I'm going to do. And you'll notice here, so I'm going to say only one of these for loops is ever going to run. And the question is why, right? So, so the question is why does only one of these loops run? I guess it's actually why does only one run? And so the answer to that is that if you notice, the length of the list is equal, right, to either the length of the first list or the second list. So min length is either this one or it's this one, right? So that's the point here. So it's like saying basically one of these loops is for j in range like 10 to 10, right? And the answer here is that you notice that if you're in the range where you start at 10 and you're going up to 10, remember you cannot include the endpoint. This will never run, right? This loop will never run. And so that's, I don't know which one it is, right? I don't know whether it's this one or this one, but I do know that one of those loops is not going to run. And that's kind of the idea, right? That's the whole point. And that's good, because then what it'll do is that it won't run the list that we've already taken everything from, and it will run on the list where we haven't taken everything from. So that's good, right? That's good. So, all right, so that's the solution to that. And then the last one is the Pig Latin one. And let's see. We have to go while we see consonants. And I let you use slices. So let's do Pig Latin, dig. And so, yeah, sure, word. So, okay, so what are we going to do here? I'm going to say vowels equals, I think you need to know all the vowels, right? And so I'm including Y, I, O, U, and Y. So that was the list of vowels that I gave you. And then what you're going to do is what's the rule for Pig Latin here? So you're going to go as long as you have consonants, right? So if it's consonants, you're going to strip them off of the front of the word and put them onto the back with an AY. So if it's consonants on the front, you move them to the back and then have a, right, so plus AY. And then for vowels, yeah, we have 2 midterms in this class. We're going to just put yay on the back. All right, so basically here, what we can do is we can say if len of word bigger than 0 and the word 0 dot lower, you know, just to be careful, is in vowels, then return word plus yay, right? That's all we got to do there. Else, right? Oh wait, this was the first midterm. Crap. I had them both open, and I didn't read, and no one told me. So that's it. Okay, the gap offset thing. That was terrible. I'm not even going to go over that. I don't care. It's terrible. Actually, no, maybe I will go over it just because, oops, someone said I was doing problems from the wrong thing. Maybe I'll do gap offset some other, what was the alphabetical thing? Oh yeah, alphabetical was just, yeah. Okay, and then gap offset, which everybody loved. That was a horrible problem. The shape problem isn't a terrible problem. Mr. Martin, be good. So, yeah, I think I'm going to do recursion. We'll get back to recursion now. I think I've spent just about long enough on homework 5. What's the average for word search? Probably low. Okay, anyway, yeah, I've wasted enough time with all this stuff. I think I've gone over enough problems. Well, let's finish Pig Latin at least, and then let me go back to recursion. So maybe for I in range word, and then if word I dot lower is not in vowels, then we keep going, right? Or I guess if it is in vowels, right, then we stop. So we basically say, then we say last letter or last consonant is equal to I. And then if we're allowed to use slices, then what we get to do is we can just do something like this. We can say word starting at last consonant to the end, plus the word at 0 up to last consonant, plus A. Something like that. Whoops, that's really bad. So that's good enough. Okay, maybe I'll do some other problems on a different day or something like that. But let me talk about palindromes. Now let's go back to recursion. So now let's actually do some recursion. So yeah, so what is a palindrome? And so the answer is that a palindrome is it's basically something that's the same way forwards and backwards. So race car, taco, cat, you know, what is it? A man, a plan, canal, Panama. Is that right? I guess we can test it with our function in a second. So something like that. What else are palindromes? Let me just Google some palindromes. Okay, so this website says pop, repaper. I'm not 100% sure. Able was I, ere I saw Elba. It's like a Napoleon reference. I like this one. Do geese see God? So, could I show a recursion display? So, okay. Oh, I like this one. I've never seen this one before. It doesn't really make any sense, but I kind of like it. Gate man sees name. Garage man sees name tag. So, all right. So let's think about how we can write a recursive function to determine if something is a palindrome. Okay, and so the answer is we've got to think about it in terms of subproblems, right? And so this is what I always think of. What's the easiest case? And the easiest case is maybe 0 or 1 letter, right? So is the letter A a palindrome? Or maybe the letter C, letter E, right? Letter F. Are these palindromes or not? And the answer is, and also the empty string. Let's also ask the same question. Is the empty string a palindrome? Well, is it the same way forwards and backwards? And the answer is yes, actually. Empty string is a palindrome, sort of, kind of, under the definition. A single letter A is a palindrome under the definition. We generally don't think of them as palindromes just because they're so stupid, but they are, they're palindromes. So, yeah. Be careful, Sean. You're treading on very thin ice. Okay. So now, how do we break down the harder problems into simpler problems? Yeah, maybe he meant it as like reverse set containment or something. Because in the end, all things are math. So how do we break things, the harder problem down into simpler problems? So let's look at hat, or let's see, pop, right? And so what we're going to do for pop is we're going to check the outer 2 letters, the first one and the last one. And then what we're going to do is we're going to ask, okay, yep, how about O? And then we say, yep. And so the answer is it is a palindrome. So basically pop turns into O. Race car should turn into ace ka, which would turn into ses or kek, I guess. And then this one turns into E. So yes. Now, if we look at it and we say, what about the word, let's say, like hat, right? Well, let's do something that, that, right? So that will turn into ha, which turns to no, right? Because the first and the last letter don't match. So what we're going to do is compare the first and last letter, not least, last letters, and then peel them off and go again. So let me show you how this works. Recursive, let's see. Okay, so now let's make the word equal to word.lower, just for the sake of simplicity, right? Actually, even better, dot split, and, well, let's not even do that. Well, let's do that, and then we can say split word equals this, and then word is equal to, so for part in split word plus equals part. And what this is going to do is it's just going to get rid of all the spaces. So, so you don't actually have to do this necessarily in a palindrome thing, but I'm doing it just to simplify our lives. So this is just simplifying our lives. Okay. And this is, actually, let's do this before we go into the function. Let's not do this inside of the function, because we don't want this inside the recursive function. Let's put this outside. Okay. Okay. And then what we'll do is we will call recursive palindrome on the new word, and that's good. Okay, so I'm even simplifying our lives further. So basically what we're going to do is we're going to test if the length of the word is less than or equal to 1, we return true, right? Because any word of length 1 or word of length 0 is a palindrome. Else, we can return the recursive palindrome. Well, let's check first. So if the word at the first index is equal to the word at the last index, which is, what is the last index? Length of word minus 1, right? Ah, crap. Get me back to here. There we go. Then we're good. Else we return false, right? If we return false, now why would we return false? So basically we're going to return false because if the two things at the front and the end don't match, it doesn't matter what else is in the middle, right? It's not a palindrome. So, and then, so these are two base cases, right? So one base case is that the length of the word drops down too low. The other base case is that the two things on the ends don't match. Then the third case is the recursive case, where we're going to return recursive palindrome. So we return recursive palindrome. And now what we have to do is we have to strip off the first and the last letter. And so in order to do that, what I'm going to do is I'm going to do something like this. I'm sorry I keep hitting page down by accident. So we're going to start at 1, and we're going to go up to, but not including the length of the word. But notice that that's actually too far. That will include the last letter, so we got to subtract 1, like that. So at every stage, let's print out the word, just so that we know what it is. And now let's run our little program. All right, let's run the program. Ooh, wonderful. Oh God, terrible. Yeah, let's run this program. So let's test pop. Oh, maybe we should print out what it returns. So no, not necessarily. I was about to do something really stupid. So pop is a palindrome, but what about, right, that's a palindrome. Race car, that's a palindrome. Something, right? Some things. So we see that here what it's going to do is it's going to split off the S's because those are going to work. But here, thing is definitely not matching. O and G, nope. So it just stops right there. So here's an example, right? If you do something like A, B, C, D, E, F, F, E, D, C, B, A, right. So this, I think, should be a palindrome, right? It is a palindrome because and it's also an even number of letters because as you go in, you're stripping them off in pairs. And actually, the even case is why I include 0 in the length here. If I said a length 0, if I said an empty string wasn't a palindrome, then even length things would not be palindromes. So let's try this. A man, a plan, Panama. False. Wonderful. What have I done wrong? Or where does it break? There. Oh, it has to be a canal. Yep. A man, a plan, a canal, Panama. There we go. There we go. That fixed it. You see, it's stripping off one letter at a time until all the letters are stripped off and we're happy, right? So palindromes are extraordinarily finicky. I like this one. Go deliver a dare, vile dog. Let's see. This is a weird one. Some men interpret 9 memos. Does the same thing work with other symbols? What do you mean other symbols? Like if we did something like 1, 2, 3, 4, 5, 4, 3, 2, 1, kind of like this. Now, Python thinks this is a palindrome. You might say it is a palindrome, or you might say it's definitely not a palindrome because it's not English letters. We didn't check for English letters. We just said, are the two things matching, right? So, you know, if you do something like that, that's a palindrome, right? It's, you know, and you might say, but that's not actually a palindrome. That's just symbols, and it should be English letters, and blah blah blah. In that case, then we would have to recode our function to explicitly reject anything that's like this. But we haven't coded that so far, so that's fine. Okay. Yep. All right. So I think we've talked enough about palindromes. And you notice here that the palindrome function is pretty simple. Basically, it just checks that if the thing is, and remember what we call this. We call this the base case. In our base case, we check that if the word's length is 0 or 1, right? If the length is, can't type a single thing, is 0 or 1, then it's a palindrome, right? By default. And then here, if the two things match, if they match at front and back, it may be a palindrome, but we need to keep checking. And then if they don't match, then nope, return false. We're done. And so you might ask, is this also a base case? Sure. And why is it a base case? Because it doesn't call a recursive palindrome. Now you might also say, well, that's not really a base case because it's in the same if statement as the recursive case. So maybe it's just a part of the recursive case, blah blah blah. I don't really care. If, I'm going to call this a base case because it doesn't make a recursive call. And I think that's the way I kind of defined it. This part of this if statement is the recursive case. This part of this if statement is another base case, right? So it's possible that you can have multiple base cases and multiple recursive calls in the same function, right? So, okay, that's one thing to think about. All right, so I'm going to show you an interesting application of recursion. And I like this example because it's a little program I wrote. Yeah, there will be coding. I may reduce it to like 4 questions rather than 5, something like that. I might try to make it a little bit more easy, but yeah, unfortunate. But as I said at the beginning of the semester, that was the one overlap that I just couldn't avoid. So that's what we have. Do I want to stop and rerun it? Sure. Okay. So I made this little program a bit ago. What's the difference between coding and programming? No idea. So basically the way that this little program works, and I'll release it on the GitHub as well, is that you can click a start and you can click the end location. And then you see that my program does this little finding thing where it kind of it traces through, and then it'll tell you this little light blue, which is the path that it found. Now it's not looking for the best path, okay? It's not looking for the best path. It's just looking for any path, okay? And so let's do it again. And let's say we start here, and we're gonna end up maybe here. So you see, it's gonna try and kind of, oh, actually, never mind. It's gonna loop to it immediately, but it didn't know anything. So let's try to make a new grid. Let's try to make a new grid. So this is a different grid. Do I like this grid? Yeah, sure. So let's start here and end here. And you notice that the black squares, I don't know, I didn't really say it, but I think you can kind of figure out the black squares are forbidden, the little white squares are permitted, right? So if you can't cross through that, and you can't go diagonally either. So you can make a program where you could go diagonally, but just according to the rules of this program, you're not allowed to go diagonally, okay? So how does this work, right? How does it work? And the answer is, if you looked at it, right, how did it know if I start here and I want to end here, right? You see that it went up first, and then it kind of stopped doing that, and then it started going down until it found the solution. Now, if you just did this iteratively, it's very, 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 very difficult. In fact, if you don't use a stack or recursion, I would say it's almost impossible to get this kind of backtracking. And what do I mean by backtracking? What I mean is that you notice that the yellow didn't get filled in. This thing didn't think, oh, I'm just going to go up here and then come back down and go here. It literally gave up on this path and it went the other way, right? So for instance here, if I do, let's reset, and then if we do the start and the end, okay, there we go. I don't want this. Let's reset, and let's put the end here. So you see that what it's actually going to do is it's going to search through the entire place here before it finally gives up and gets us to our answer, right? So it's going to search through this whole blob, but you notice it doesn't take any of that part for its path, right? And so how was I able to get it to do that, right? And the answer is recursion. So let's go through pathfinding, and let me show you how this thing works. And then maybe next time we'll do a little bit more on that, and then we'll talk about classes and stuff. And you can play with this thing yourself. The secret is that R resets the grid, and G generates a new grid. So I know this program is not exceptionally well documented, but whatever. So the point here is, this is really the function where we searched for the path. So let me show you how this works, okay? So some of this stuff is useful for general pathfinding, and some of this stuff is not useful for general pathfinding. Like, for instance, here, the self.gridCanvas.item configure. This is just changing the thing to a yellow color. Does it also use the quickest path to find, or does it find the quickest path? No, it basically explicitly does not care. So there's two. Okay, let me put it to you this way. When you're doing pathfinding, there's a balance between these two things. Finding a path quickly and finding the shortest path, or the fastest path. And those are two very different tasks. So this program basically, and because it's the much simpler thing to do, this does what's called a depth-first search, which what it does is it generally finds the answer quickest. But the answer that it finds isn't the best, usually, right? And there are examples where it could find both the best answer, the quickest, but so the point is that what I teach, at least in this class, is generally a depth-first search. There's something else called a breadth-first search, which finds the shortest path, but it actually takes your algorithm longer to run, right? It takes more steps to find the best path than it does to just find a path, right? So that's just something interesting to think about. Okay, so basically, how does this work, right? And let's keep documenting this thing. So here's how it works. Basically, here's my base case, right? If we're at the destination, right, current is equal to self.destination, which don't worry about the self right now. Just think about it if current is equal to destination, right? Then we return a list containing current. And the reason why I do that is if you notice here, under the hood, right, in secret, this program is actually displaying the path that it found. It's not just displaying it visually, it was actually displaying it here as well. So I wanted to know what path we took. And so this tells me that. Okay, so then what I do is, because I don't want to use anything forbidden, I just said x is equal to current 0, y is equal to current 1, because current is a tuple, right? Is a tuple with two elements, right? It represents x, y. Okay, so now what I'm going to do, ignore the visited thing for just a second, ignore that for just a second, okay. And ignore this part. So ignore everything here. Ignore the man behind the curtain. And the reason why I say to do that is because, that's what I say. So ignore this part here for just a second. And now let's look at this part. Let's look here. And so why do I want to look here? So what happens, here's all the different recursive cases. They're all basically the same, but let's talk about this case in particular. So what I do is I check to see if 0 is bigger than or equal to x minus 1. And so the reason why I do this is because I want to check that if I move to the, if I move to the left, I think, is that what this is doing? Actually, no, this is moving up. So basically subtracting 1 from the x is moving up. Right, and so basically that's what this case is trying to move up. And if it can move up, right, if we're not at the top, because if x is already 0, then subtracting 1 from x will get us -1, and then trying to stick in the grid of -1 will give us problems. Actually, it won't give us problems, but it'll actually give us like a circular toroidal grid or something like that, something not particularly good. So, and ignore this self.visited thing for just a second. So basically, if the self.grid x minus 1 y, basically what this means is if this comes back as true, right? That's the whole point, is like what is this testing? If this comes back as true, then we're good, right, to go there. If it comes back as false, means forbidden. Okay, so then what I do is I say, okay, now search for the path, but now instead of starting at x, y, start at x minus 1 comma y. So that's the whole point here. And then if the path comes back, right? So what happens, what does this mean? So if the path means that the path wasn't just returned as none or empty list or something, right? And in that case, what that means is that we found a path, right? If we didn't find a path, then this thing is just going to return empty list, okay? And so that's how we can detect which case we're in. So if we're in a good case where we actually found a path, then what you do is you tack on the current thing and return the rest of the path, which is a list, right? You notice that the path is just a list of tuples, and so here we're going to return the current plus the path. And then basically this repeats, right? Instead of moving down or moving up, this is moving left. X plus 1, this is moving down. And y plus 1, this is moving right. And so the idea here is what you're going to do is first you're going to try to move up. And if that works, then you're good. Then you're going to try to move left. And if that works, then you're good. And then you're going to try to move down. And if that works, then you're good. And finally, if you're going to try to move right. And if that works, then you're good. Otherwise, yeah, I might be able to do that next time. I think I'm going to have to talk about all that next time. Actually, I'm not sure if I can debug it since it's a GUI program, but you know what? Why not? Let's try it. Let's see what happens. Okay. Let's start the debug here. And let's debug. And so here's the debug process. Okay. So let's give it an easy path to find. Let's say we're just going to go straight up. And now we're at the breakpoint, right? So now we're there. Okay. So let us step. Let's see what happens. So it's going to go self, blah, this kind of stuff. All right, so now it's going to try to move up. Whoops. Why didn't it do that? Okay. Why couldn't it move? Where did I pick the... Oh, I see. Okay, so... No? Oh, maybe I actually have X and Y correct. So actually instead, this isn't moving up, this is moving left. This is moving up. This is moving right. And this is moving down. I think I might have actually fixed it so that it's correct. So here, let's keep stepping, right? So basically what's happening here is we're setting these again. And then here we're going to go visited equals true. And then here, fill the thing in yellow. Oh crap, let's step out of this. we don't care about that. You notice that it's filled the thing in yellow now. So now here we're going to do this. Let's step over that. Step over the sleep function. And then here what we're going to do is, I think we can't move left. So now we're going to try to move down, or I'm sorry, move up. And so now it's going to try to search for the path, but now instead of being at this position, or being at this position, it's going to move up and be at this position. So now here it should be, X should be what? 0 and Y should be 3, right? Because we're at X position 0, Y position 0, 1, 2, 3. And this is where we are. And then you notice that it's going to mark it as visited. It's going to do this. It's going to color it in yellow, right, which is our current position. We're going to sleep. That just prevents it from drawing all at once. It just slows our algorithm down so you can see what's happening. And then here, can we go left? No. Can we go down? Yes. Do that, right? Keep doing it. Whoops, didn't mean to step into that. Step out of that. Step out of that. Okay. Step over those things. Okay, and then finally, I think we're almost to the position, right? So now here we're at X equals 0, Y equals 1. Step over, step over, step over, step over, step into. Here we go. And then finally, so now what we see is that where are we? If the current is equal to the destination, return current. That's what it does. And then it's going to pop out of this function. And now remember where it went back to. It went back to the recursive call where we were here. So basically what just happened is we went to the answer. It said, oh, we're at the answer. So we're done. So now pop off the recursion. And then now we're going to go back to here where this function is waiting. right? This function is waiting here because it's saying, I'm waiting to assign this path. The path comes back to me and it's not empty, so we say, okay, cool. The path isn't empty, so we're going to return this. And so now you see that, let's see. Okay, so now we're going to assign path, and you see path is already 0, 1, and 0, 0. And now we're going to add 0, 2 to the mix. Well, we're going to add it and return it, so let's see. Current. Okay, let's go one more line. So here, path is now 0, 2, 0, 1, 0, 0. And then what we're going to do is we're going to return this. And the path is now 0, 3, 0, 2, 0, 1, 0, 0. And then finally, we're going to, let's see. We have 0, 4, blah, 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 blah. Return this. And then, oh, Lord. Then it basically returned the result. This is the return the result to here. So then I guess we can, you know, resume program at that point, right? So notice that this is some code that you should not necessarily be messing with. But this code, on the other hand, this is the part that, like, basically the function that's important here is the search for path function, okay? The rest of this stuff is just for the GUI interface to work, right? Like, all the rest of this crap is just to get this, this stuff to display, okay? So yeah. All right, I know I spent way too long on this. I'll go over, I'm going to write a little bit of pathfinding next time, so we'll actually rewrite this function, and I'll show you why you need the visited stuff, and I'll show you, basically, I should spend an entire day's lecture on just particularly grid problems. Is it possible to do recursion on homework 5 with the matching shapes? Yes, but I wouldn't. I think it is more trouble than it's worth, as you say. Because I can't think of an obvious way to do it. The obvious way, yeah, this is definitely branching recursion, because you see here there's multiple different recursive calls, so it's possible that you can go left and not find a solution, and then you can go up and not find a solution, and then you can go right, and maybe you find a solution, and then you start returning, right? So that's why this is branching recursion, because you can go multiple different paths. Yeah, whenever you can go multiple different ways, it's definitely branching recursion. No, I just want to run the program. I don't want to actually stop it. Okay. Because if you notice here, what happened here is it went this way, this way, this way, and then it returned empty, return empty, return empty, return empty, because it realized that it was never going to find the answer going this direction. So let's see how bad this is. You're going to see a pretty bad path here. The answer is kind of yes, but also kind of no. Like, eventually you'll have to be able to sort of reproduce this one function, right? This one function. You're not going to have to reproduce all the graphical stuff. So just this part is what you need. And I'm going to do more explanation of what the stuff is. So what we have covered so far is how this is moving left, moving right, moving up, down. But what we haven't talked about is how visited works, and we haven't talked about some of the other things. But basically, I'll talk about visited next time, and that'll be that. Okay? And then we'll recode this to some degree. All right. So I'm going to let you go now, because I've kept you way too long. But also, I think, yeah, hopefully today wasn't a complete waste, that we covered some of the homework problems and some of the exam problems and stuff. Okay. All right, time to go. Where's OBS? There's OBS. Let's do the outro.